students, welcome to Sunil's tutorial. I'm Sunil Barwani and today we'll be doing this chapter called as current electricity. Now, let's try to understand what is Seebeck effect. Seebeck effect. Now, we know that a thermocouple is formed by joining two wires of different metals from end to end. A thermocouple is formed by joining two wires of different metals from end to end. Right? Now, Thomson-Johann Seebeck. He's a German physicist. In the year 1821, discovered that if the two ends of the junctions of the thermocouple are kept at different temperature, if the two ends, if the two junctions, not two ends, two junctions of the thermocouple, are kept at different temperatures, an electric current begins to flow in the circuit. Right? An electric current begins to flow in the circuit of the two different conductors. Fine. Now, a magnetic needle, if it is held close to the circuit, shows deflection, right? Or a galvanometer connected in the circuit also shows deflection, which indicates the presence of an electric current in the circuit. The EMF developed due to this electric current is called as thermoelectric EMF or Seebeck EMF. I can say that the EMF so developed is called thermocouple EMF or Seebeck EMF. Right, and this effect is called as thermoelectric effect or Seebeck effect. This effect is called as thermoelectric effect or Seebeck effect. Right? Now, let's see how does this occur. Suppose if I have one wire or one conductor of one metal and I have another conductor of another metal joined end to end. Let's assume I put a galvanometer here. This is a galvanometer connected here, right? This is, say, iron, and let's assume that the other metal is copper. Right? I'm keeping one of the junctions A hot and the other junction B cold. Right? So So if the two junctions are kept at different temperatures, what Seebeck observed is that electric current begins to flow. Seebeck observed that electric current begins to flow in the circuit, right? And this effect is called as Seebeck effect. The electric current then produces an EMF. So if I have a thermocouple which is formed by two different metals, it's formed by the junction of two different metals. If I keep the two junctions at different temperature, automatically EMF is generated. Right? Do you get this thing here? So thus the phenomenon of production of EMF in a thermocouple when its junctions are kept at different temperatures is known as Seebeck effect. Let's say the phenomena of production of EMF in a thermocouple when its two junctions are kept at different temperatures is known as Seebeck effect. Right? So do we understand what is Seebeck effect? Now let's see what are the observations of for Seebeck effect. Observations. Right? Now it has been found that the thermocouple EMF that is developed is extremely small. The thermocouple EMF which is developed is about 7 microvolts for every 1 degree difference in temperature. If there is a 1 degree difference in temperature, then you would have say about 7 microvolts of EMF that would be developed for a iron and copper thermocouple, and if it is tin and bismuth, then the EMF that would be developed would be say about 100 microvolts. So in all and all, what we realize is that the EMF which is developed is extremely small. So the first thing that you understand about Seebeck effect EMF is that the thermocouple EMF developed is very small. Right. Next, the magnitude and the direction of the thermocouple EMF depends upon the nature of the material used for the thermocouple and the temperature difference between the two junctions. Right. So depending whatever are the material and what are the temperatures at two junctions, that will determine my direction of the current. Right. So I can say that the magnitude. Obviously, the magnitude of EMF depends upon the difference in temperature and the material used. So, the magnitude and direction of thermocouple EMF depends upon the nature of material. Depends upon the nature of material used for the thermocouple and the temperature difference between the two junctions. Temperature difference between two junctions. These are the two parameters on which the magnitude and direction of current would depend. right? Seebeck effect is reversible. That means the direction of the current can be reversed if the hot and the cold junctions are interchanged, right? So the direction of the current depends upon which junction is the hot junction and which junction is cold junction. So I can say that Seebeck effect is reversible. Fine. Now, so these are your observations of Seebeck effect, right? Seebeck also found out that the thermoelectric properties for different pairs of metal can be arranged, and the pairs of metals can be arranged in a certain order, which he called as the thermoelectric series. So for a particular pair of metal, for every 1 degree rise in temperature, a certain amount of EMF only would be generated, and he arranged this pairs of metal in the increasing order of their EMF produced for every degree rise in temperature. He called this particular series as the thermoelectric series. Fine, do you get this in clear? Besides that, if current I is flowing through the thermocouple and R is the total resistance of the circuit containing the thermocouple, then the amount of energy would be I square R. It should be I square RT, but I am considering only 1 second, so T would be 1. So the amount of energy is, that is the amount of energy that would be converted into heat per second. I square R would be the amount of heat energy that would be converted into heat per second, right? Which makes us understand that there must be some source of EMF in the thermocouple which is causing the flow of current, right? If there is flow of current, see, we know that if there is EMF, there would be some amount of heat energy that would be generated. If there is some amount of heat already present, if there is some amount of difference of temperature already present between the two junctions, that would lead to the production of EMF that would flow through the circuit. Fine, do we get this thing here? Okay, so that was Seebeck effect. Next, let's move on ahead. Let's see Peltier's effect. Now, this particular effect was discovered in 1834 by a French scientist by the name Jean Peltier, and he found an effect which was the converse of Seebeck effect. Now, in Seebeck effect, what you do is you take a thermocouple, you keep the two junctions at different temperatures, and you see that EMF flows through it. Now, if I do the reverse of this, if I take a thermocouple and if I pass an EMF through it, what we find out is that the two junctions then develop different temperatures. So it is exactly the converse of Seebeck effect. In a thermocouple, if an EMF is connected to a thermocouple, then what is observed is that the two junctions would, there would be a temperature difference between the two junctions, where one junction would become relatively hot as compared to the other junction. Fine, do you get this thing here? So according to Peltier's effect, yeah.
So what did you mean when you said Seebeck effect is reversible?
In Seebeck effect, what do? You keep a difference in the temperature between the two junctions, which causes the EMF to flow. This is exactly converse. I am passing EMF through the thermocouple, and this passage of EMF through the thermocouple brings about a difference between the temperature of the two junctions. That's the reason why we call it as converse. Right? Yeah. You wanted to ask me something else? Okay. According to Peltier's effect, if the junctions of a thermocouple are at the same temperature, are at the same temperature and current is passed round the circuit, and current is passed round the circuit and current is passed round the circuit of the thermocouple, then heat is produced at one junction and absorbed at the other junction. Then heat is produced at one junction and absorbed at the other junction. Right? That is, one junction is heated and the other junction is cooled. That is, you will have one junction will be heated and the other junction would be cooled. Now this effect is also reversible. That means if I change the direction of the current, the junction which is being cooled will become hot and vice versa. Right? So I can say that this effect is reversible. Fine. So, do we understand what is Peltier's effect? Now, I'll just show you this with the help of a diagram. Let us consider that I have a wire here. This is, say, an iron wire, right? And let us connect a copper wire to this. Let us put EMF here. No, this is copper wire. Okay, this is junction A, this is junction B, right? Now, since EMF has been there is a battery source connected in the circuit, current would flow through the circuit. So let's assume that this is the direction in which current is going to flow. The conventional current will flow from the positive terminal to negative terminal. What we observe is that junction B is cooled, whereas junction A becomes hot, right? So, if I consider a copper iron thermocouple with their junctions at the same temperature, and if the junctions are connected in the circuit and current is passed through the thermocouple, it is observed that heat is evolved at junction A and absorbed at junction B. As a result, junction A becomes hot and junction B becomes cool. Now, if I reverse the direction of current, then what would happen is that junction A will become cool and junction B will become hot. Question: why does this happen? Right? Now, I can say that when two dissimilar metals are joined end to end, when two dissimilar metals are joined end to end, EMF exists across each of the two junctions of the thermocouple. EMF exists across each of the two junctions of the thermocouple. This I had explained to you when I explained to you what is a thermocouple and how it is formed. Because the two are going to have different coefficient of resistance. As a result, an EMF is going to be developed at the junction. So, an EMF is going to be developed at the junctions of the two couples, at the thermocouple. That is, a contact potential is going to be established at the junction. Now, that is, I could say, at a contact potential would be established or is established at the junction. the junctions. So you would have a contact potential that would be established at the junctions. Now, this is because the potential of one metal is greater than that of the other. This is because the potential of one metal is greater than the other. Right? Now, in the case of the diagram that I have shown you, if I consider a copper and iron thermocouple, the potential of iron is greater than that of copper. Right? So, when a current is passed through a thermocouple, let's consider this case. In case of copper iron thermocouple, the potential of iron is greater than that of copper. The potential of iron is greater than that of copper. Right? So as a result, at junction A, current flows from copper to iron, that is, it flows from higher potential to lower potential, right? So when it is passing at junction A, current flows from iron to copper, right? That means it is going to flow from a higher potential to a lower potential. That is, it flows from higher to lower potential. It flows from higher to lower potential, and therefore energy is given out. And therefore energy is given out. Now, as energy is given out, that is evolved at this junction, and therefore it becomes hot. Right? Energy is given out, and junction A becomes hot. Right? That is the reason why junction A would become hot. Next, at junction B, current would flow from copper to iron. At junction B, current flows from copper to iron. As current flows from copper to iron, that means it is going to flow from a lower potential to a higher potential, right? Copper to iron, that is, it flows from lower potential to higher potential. Now, as it flows from lower potential to higher potential, energy is required for this purpose, right? The energy required for this purpose. Say that the energy required for this purpose is absorbed by the junction. Is absorbed by the junction. Right? As a result, what would happen? Junction B is cooled. As a result, junction B is cooled. Right? So that is the reason why one junction would become hot and the other junction would become cooled, right? So, do we understand Peltier's effect? Now, in Peltier's effect, suppose if I change the direction of the current, then the effect would be changed. The effect is reversible. That means if the direction of the current is reversed, then heat is evolved at the junction, which was heat is evolved at the junction at which it was formerly absorbed, and vice versa, right? So I can change this effect. Okay. So do you understand Peltier's effect? Next, let's understand what is Peltier's coefficient. What is Peltier's coefficient? Now, Peltier's coefficient, it is defined as the amount of heat absorbed or evolved at a junction when 1 coulomb of charge flows across the junction. Right? Peltier's coefficient is defined as the amount of heat absorbed or evolved, as the amount of heat absorbed or evolved, amount of heat absorbed or evolved at a junction due to Peltier's effect when 1 coulomb of charge passes across the junction. When 1 coulomb of charge passes across the junction, right? 1 coulomb of charge passes across the junction. So thus I can say Peltier's effect, this is denoted by pi, is nothing but Peltier's heat divided by the charge flowing. Peltier's heat divided by the charge flowing. This is your Peltier's coefficient, right? So Peltier's coefficient depends upon the nature of the metals forming the thermocouple and the temperature at the junction. What will be the SI unit for this? The SI unit, heat upon charge, so that means it should be joules per coulomb, right? Now, let's also assume that if the temperature of the cold junction of the thermocouple is theta and that of the hot junction is theta plus d theta, if the temperature of cold junction is theta and that of hot junction is theta plus d theta, right? Let's also assume that dE is the amount of thermo EMF produced. dE is the amount of thermo EMF produced. If dE is the amount of thermo EMF produced, then it is found that I can say phi upon theta, right, is nothing but dE upon d theta, right, where dE by d theta represents the thermoelectric power or the Seebeck coefficient, where dE upon d theta represents thermoelectric power, or which is also called as the Seebeck coefficient. Fine. So thus Seebeck coefficient is nothing but pi upon theta. Therefore, I can say Seebeck coefficient is Peltier's coefficient divided by the temperature at the pole junction. Right? So, do we understand what is Seebeck coefficient? So, I can therefore say that in Peltier's effect, the heat absorbed or evolved at a junction is directly proportional to the current flowing through that junction. I can change the temperature of the junction by changing the current flowing through a junction, right? So it is directly proportional to the current flowing through the junction, and it is independent of the resistance of the circuit. You can see that in Peltier's effect, resistance has no role to play, right? So thus I can say that the heat evolved or absorbed at a junction is directly proportional to the first power of current, which is contradictory to Joule's effect. Joule's effect says that for heat to be produced, you require resistance. Joule's effect says that the heat produced depends upon the resistance, whereas here in Peltier's effect we see that the heat is produced and resistance has no role to play in the heat that is produced. Okay. Next, let's move on to another concept now. Let's see Thomson effect. Now, in 1851, Lord Kelvin, or William Thomson as he was known, argued that each element of a single conductor can behave as a source of EMF when a conductor has non-uniform temperature along the length. So he said that if you have to produce EMF, you can just use a conductor to produce EMF, so long as when the conductor has non-uniform temperature along its length, right? That means if the two ends of a single conductor are maintained at different temperatures, an EMF would be developed between the ends of the temperature. All I need to do is take a conductor and make sure that the two ends of the conductor are maintained at different temperature. Automatically the conductor would produce EMF, and this EMF is called as Thomson's EMF, right? So I can say that if Thomson stated that each element of a single conductor, can behave as a source of EMF. Behave as a source of EMF, right? Can behave as a source of EMF when the conductor has non-uniform temperature. When the conductor has non-uniform temperature, along its length. Right? Thus, if the two ends of a single conductor are maintained at different temperatures, if two ends of a conductor are maintained at different temperatures, then an EMF is developed between the ends. right? This EMF is known as Thomson EMF. This EMF is known as Thomson EMF, right? So thus I can say that if a steady current is passed through a conductor, such conductor that is heated unequally, and absorption and evolution of heat takes place along the length of the conductor. The absorption or evolution of heat along the length of the conductor when current is passed through an unequally heated conductor is known as Thomson effect. So I could say that if steady current, let's do it with steady current, if steady current is passed through a conductor, is passed through such a conductor, if steady current is passed through such a conductor that is heated unequally, and absorption and evolution of heat takes place along the length of the conductor. And absorption and evolution of heat takes place along the length of the conductor. And absorption and evolution of heat takes place along the length of the conductor, right? So thus the absorption or evolution of heat along the length of the conductor when current is passed through an unequally heated conductor is known as Thomson effect. So what is Thomson effect? It is the absorption or evolution of heat. It is the absorption or evolution of heat along the length of conductor, when current is passed through an unequally heated conductor, when current is passed through an unequally heated conductor is known as Thomson effect. So if I heat a conductor unequally and if I pass current through it, right, there would be absorption or evolution of heat along the length of the conductor, and that would be called as Thomson effect, right? Now let's consider how this happens and why this happens, right? Let's consider a copper wire. This is Cu wire. Let's consider junction A and junction B, right? Let's assume that junction A is kept hot whereas junction B is kept cold, right? So in that case you would have heat evolved, right? Now question, what would happen? This is the wire, right? One of the junction, that's your junction A, which is your hot end, is going to be maintained at a higher potential as compared to junction B, which is your cold end, right? So as a result there would be decrease in heat that would cause the heat evolution. Thus heat is going to be evolved, right, through the copper wire. So a copper wire with one end A hot and the other end B cold, that means it is not uniformly heated, right? Now if current is passed from one end to the other end along the length of AB, it is observed that heat is evolved along the length of the conductor. Heat energy is given out along the length of the conductor, right? On the other hand, if current is passed from B to A, from junction B to junction A, then heat is absorbed along the length of the conductor. Now question, why? Why does this happen? This is because the hot end of the wire is always at a higher potential as compared to the cold end of the wire, right? Therefore, when the current flows from end A to end B, it flows from higher potential to a lower potential. End A is at a higher potential. Let's consider this is potential. It flows from a higher potential to lower potential, right? And hence heat is given out, right? So do you understand why heat is evolved? Let's write this down. Consider a copper wire with end A hot and end B cold. Right? Now, if current is passed through, if the current is passed from end A to end B, if current is passed from end A to end B, if current is passed from end A to end B along the length of AB, it is observed that heat is evolved along the length of YAB. It is observed that heat is evolved along the length of YAB. Length of wire AB, right? Now, why? Because hot end of the wire is always at a higher potential than the cold end. Hot end of the wire is always at a higher potential than the cold end, right? Hence, I can say that when current flows from A to B, therefore, when current flows from A to B, that is from end A to end B or from terminal A to terminal B, it flows from a point of higher potential to a point of lower potential. It flows from a point of higher potential to a point of lower potential. It flows from a point of higher potential to a point of lower potential, right? And hence heat is given out. right? Now, similarly, if I had current flowing from B to A, heat would be absorbed in that case. Fine, do we get this thing here? So, substances that behave like copper, right? Substances that behave like copper are said to have positive Thomson effect. That is, when current flows from higher potential to lower potential, heat energy is evolved, right? Now there are certain substances like say iron, cobalt, bismuth, nickel, in which case heat is evolved when current flows from the cold end to the hot end. Here heat is evolved when the current flows from hot to cold. But there are certain other substances where heat is evolved when current flows from the cold end to the hot end, right? Such substances are said to have negative Thomson coefficient. I can say substances in which heat is evolved when current flows from hot end to cold end, from hot end to cold end are said to be have positive Thomson effect. Are said to have positive Thomson effect. Right? Now, there are certain substances in case of which case heat is evolved when current flows from cold end to the hot end, from cold end to the hot end, are said to have negative Thomson coefficient, or are said to show negative Thomson effect. Right? So you can have substances having positive Thomson effect and you can have substances having negative Thomson effect. Now let us assume that d theta is the temperature difference between the ends of a small section of a conductor. If d theta is the temperature difference between ends of a small section of a conductor, right? Then Thomson's EMF is given by sigma d theta. That would be the EMF that would be generated, where sigma is called as Thomson's coefficient. Fine, do we get this thing here? So the existence of EMF is indicated by the heat absorbed or evolved per unit quantity of charge transferred. How do I know that there is EMF? The fact that heat energy is absorbed or evolved heat energy cannot be absorbed or evolved unless and until there is EMF produced. So I can say that the existence of EMF is indicated by heat absorbed or evolved per unit quantity of charge transferred. Right? That's the reason why you have EMF produced. So like Seebeck and Peltier's effect, Thomson's effect is also reversible, right? So the Thomson's coefficient depends upon temperature and the material of the conductor. How much EMF will be produced depends upon what is the temperature difference between the two ends of the conductor and what is the material of the conductor. Is it a positive Thomson effect material or a negative Thomson effect material, right? Thus, on the basis of this, I can say that Thomson's coefficient can be defined as Thomson's coefficient can be defined as the EMF setup between 2 points of a conductor. EMF setup between 2 points of conductor, which has a temperature difference, of 1 degree Celsius. So Thomson's coefficient can be defined as how much EMF would be developed between 2 points of the conductor if the temperature difference between the 2 points of the conductor is 1 degree. So thus I can say Thomson's coefficient is nothing but dV by d theta, right? Where dV is the small potential set up between the 2 points of the conductor. dV is small potential developed between 2 points of a conductor and having a temperature difference of d theta. Fine, do we get this thing clear? Now the SI unit for Thomson's coefficient is volt per degree Celsius. SI unit for Thomson's coefficient is volt per degree Celsius. Fine, do we get this in here? Now, Thomson's effect is found to be nil for lead. It means that no heat is evolved or absorbed when current passes through unequally heated rod of lead. It is due to this reason that lead is used as a reference material for thermoelectricity. So why is lead used as a reference material for thermoelectricity? If the two ends of lead are kept at unequal temperatures, then no current will flow through them. No heat will be absorbed or evolved when current flows through them. Right? So I can say that Thomson's effect is found to be nil for lead. Thomson's effect is found to be nil for lead. Right? That means no heat is evolved or absorbed no heat is evolved or absorbed when current is passed through, when current is passed through an unequally heated lead and unequally heated lead rod, right? It is due to this reason that lead is used as a reference metal. It is due to this reason that lead is used as reference metal in thermoelectricity. Fine, do we get this thing here? So, therefore, thermocouples using lead material are used for determining Thomson's effect. Right? Now, let's consider this. I can say that it can be proved that Thomson's coefficient of a material of the conductor, sigma, is nothing but minus theta d square E upon d theta square. Right? Thomson's effect sigma can be written as minus theta d square E upon d theta square. Now we know that, but Seebeck effect or Seebeck's coefficient S is nothing but dE by d theta, right? Thus I can say that if I differentiate this, I will get ds by d theta is nothing but d square E by d theta square, right? So in which case I could therefore say, substitute this value there, I could say that Thomson's coefficient is minus theta ds by d theta, right? So that's my relationship between Thomson's effect and Seebeck effect. Fine, do we get this thing here? Right, okay, we'll stop this here for the day. Thank you very much.